No, en inglés,
Wow.
porque hay una persona que no habla muy bien, no practicó español fin de semana. Sí, podemos empezar. Yo creo que nadie más va a venir. 1, 2, 3 y 4.
Okay. Welcome everyone for the seminar. This day we have the honor to present Sir Mike Kowalczyk. I don't know if the pronunciation correct. Who told us about asymptotic stability of kinks in the hot energy space.
Okay,
Welcome.
thank you. So I will give the talk in English because there are some people who don't speak Spanish very well. They speak some Spanish, but not very well. So maybe I don't speak Spanish very well either. Okay, so this talk is based on basically two joint works, one with Ivan Martel and Claudio Muñoz, and one with Ivan Martel. And there is a gap of 10 years between them. And the second work, I think, is about to appear. And the first was already published a long time ago. Okay. So what I'm interested in is this kind of nonlinear wave equation. Okay. This is a wave equation in which in one space dimension always, and with some initial data in Cauchy data. And this is a family because what I'm interested in are various functions W, various potentials W. So in general, W, I will give examples, is a non-negative function, and it's called multiple well potential. So there is a more convenient form to write this single equation as a system. And to begin with, and this is very important, it's very easy to notice that there are two quantities that are conserved along the flow. One is the energy, and the other one is momentum. Of course, they are formally conserved along the flow. You have to differentiate this energy with respect to time, use the equation, and you get zero. And the same with the momentum. Okay, so the energy and momentum are conserved. All right. So what are the examples of this potential W? So the first example is a classical sine-Gordon potential. So it's a periodic potential. Oops. So let's see. So it's 0 at 0 and 0 and 2 pi. And it looks like this. And it's periodically repeated. So this will be 1 minus cosine phi. This is phi. The other potential is what is called phi-4 potential. It's phi-4 because this is a fourth order potential. And it's also classical potential. It's very easy. This one is not periodic. It just looks like this. Okay. And there is, in fact, a whole hierarchy of this kind of theories, of this kind of potentials, which are of 4n order, okay, or 4n plus 2 order. These are the general formulas, okay. This is called P-phi2 hierarchy. And what is interesting is that, let's say, for this potential, when n is equal to 1, it's a phi-4 potential. When n goes to infinity, just by product formulas, these potentials go to the sine Gordon potential, okay, as n goes to infinity. And there are all these intermediate theories, let's say phi 6, phi 8, phi 10, and so on, okay? So these are kind of potentials I'm interested in. And by the way, this is very important. This problem is, I will explain why, belongs to the family of problems in general for any of these kind of potentials, multiple well potential, okay, and with W non-negative, belongs to the family of problems which are called defocusing, okay? So in the nonlinear wave equation, there are basically two big families. One is the family of problems which are focusing, and the other one is defocusing, okay? So these are defocusing problems. So what are the known solutions, stationary solutions that are interesting? So there are solutions called kinks. So kinks is a heteroclinic. So you see, you do the phase plane analysis, and this is very easy. For instance, for 5-4 model, you do phase plane. Oops, no, this is not a good picture. And by the phase plane analysis, you find two solutions that connect -1 and 1, okay? They are heteroclinic solutions. So if you draw a picture of them, one looks like this. It's an increasing solution. It's called kink. And there is another one, which is simply, so kink is the one that goes from -1 to 1, and there is the one that goes from 1 to -1. So like this. And so the one that goes from 1 to -1, okay, in this theory, it's called anti-kink. Okay. So these are typical solutions. So for 5-4, you solve explicitly the problem, the stationary problem, and you find tangent hyperbolic. For sine Gordon, you find another, okay, for arctangent E to X. And for these other models, okay, for phi6, for instance, you can find explicitly still explicit kink. For the others, no, they are sort of mysterious in some sense. Now there are other interesting solutions. So there is a solution called breather, and this is a very particular solution for the sine Gordon equation, and it is believed that this kind of solution only exists for sine Gordon equation in some sense. And this solution is also given explicitly, and it's not a time independent solution. It depends on time in a periodic way, okay, and it's localized in space. So forget about the arctangent and think of A very small. So this solution, like, I'm running out of space, so this solution looks like this. It's let's say for t equals 0, it's like cosine hyperbolic when A is very small. Its amplitude is very small, okay? It's because A squared plus B squared must be 1, so B is morally 1. So the amplitude here is A, essentially. And it oscillates in time. So later in time, maybe it will be 0 when t is equal to pi over 2. And then it will be negative, symmetric, and then it repeats itself, okay? It's called breather, this kind of solution. All right? So then it turns out that in the sine Gordon theory, you can make, in certain sense, superposition of kinks and breathers. and the result is what is called wobbling kink. So wobbling kink will be a kink that is somehow periodic. It oscillates, it wobbles, okay? So let's say for some time it looks like this. Then later, asymptotically, it's still, let's say at minus pi and pi or something like this. But it looks like this. Maybe later in time, it looks like this. It's periodically, okay? And this kind of solution is explicit as well, but it's a long formula. So I don't want to write this formula because it's too long. Yes? Kink is a functional, but of course, you can make it flow, but this is another story. You can translate it, or you can, what is called, in fact, you make Lorentz transformation, okay? And the kink becomes a moving object, but this is another theory. Right? Let's say Hane knows about this because we worked on this with Hane. But here I insist that I only work in odd perturbation. So in particular, kink is odd, and wobbling kink is also odd for all times t. Okay. So what is the point in working with odd perturbations only? The point is that if I work with odd perturbations, I fix zero because an odd function has to be 0 at 0, and I don't allow exactly, I don't allow the kink to move, and the perturbations are kind of fixed to 0. That helps a lot and makes things somehow easier. Okay. So let's talk about the energy space. So the energy space is the space in which I consider the perturbations. So not only I consider the perturbations to be odd, but I consider them to be in the energy space. So what does it mean? It means that I take perturbations of the kink, okay, U and U1 and U2, which are such that it's the H1 norm of U1 is finite and L2 norm of U2 is finite. Okay, so I know this this way. So this is the initial data. So my initial data is a perturbation of the kink. It's an odd function of x, and it's in the energy space. So if I assume that the initial data is in the energy space, then the solution, in fact, is in the energy space, has finite energy, okay? It's global in time, and it's odd, because oddness is preserved by the equation, okay? And not only that, if I assume that the initial data is not just less than some number, but it's small, then the solution in the same norm will be small. This is called stability. So it is known that kinks are stable, and here is partly Brazilian mafia, okay, and partly not so Brazilian mafia. But anyway, Henry was at the time in Brazil, I believe in Sao Paulo, and they proved this in the sorry, in the 80s. Okay. Yes. No. This is the kinetic energy plus potential energy, the total energy. Okay. So this is the conserved object. No. So the question I want to address is whether the kink of the phi4 model, first of the phi4 model, is asymptotically stable in the energy space. So now the problem is to to be precise about what does it mean asymptotically stable, because because it's a wave equation. It's not, the energy does not dissipate, it just radiates, it spreads somehow. It's not a priori obvious what does it mean asymptotically stable, okay? So as I said, the energy is conserved, and therefore we cannot say that the energy in this sense, or the norm in this sense, goes to zero, okay? This is impossible, because if this were true, then the initial data is just the kink, nothing else, okay? Now, there is another problem that I already mentioned, that if I want to ask about the stability, asymptotic stability of the kink, then this question only makes sense in the odd space where I do not allow the kink to move. Because as soon as I depart from the odd space and I assume that the initial data is just any function, just general function, maybe small, but general function, the kink will immediately start to move. And this is because of the Lorentz invariance, okay? So I don't want to talk about this too much, but Lorentz invariance is like the Galilean transformation, but in the relativity theory, okay? So what would be the most interesting thing to say? The most interesting thing to say would be if I start with a small data, so U is a small perturbation of H0, okay? Then small perturbation in this energy space, okay? Then later in time, L infinity norm of this perturbation goes to zero, okay? That would be the most, I think, interesting for physicists, but this is a hard problem, and in fact, it's an open problem. So a weaker statement would be to say that the L infinity norm, but not on the whole real line, but on a portion of a real line, let's say for any finite interval goes to zero, okay? And that is somehow easier, because what you look at is a window, okay? Is a finite space interval window around the kink, not the whole space. In fact, this is true, and this is a result of another of a statement that will involve local energy norm. So this is like the energy norm. So it's like this norm H1 cross L2, but over finite time interval, over compact interval. Okay. So again, we look at the energy norm, but on a window. And this is in this sense, in the sense of this norm, that I will speak about the asymptotic stability. Okay. So what is the statement? So what I will first talk about is asymptotic stability of the phi4 model in the odd energy space. So we write the phi4 model, okay, as in this way. So there is this is a system, 4 perturbations around the kink. So you have a linearized equation, okay, linearized equation. This is the linearized operator around the kink, and the nonlinear part, okay, H is the kink. Yeah. So this is explicit. It's very easy because the nonlinearity is explicit. And the theorem says the following: if epsilon is small, and I take the initial data, which are odd in X, and they're in the energy space, and they're small in the energy space, notice that this is the global energy space for all real line, then the limit, as time goes to zero, of the local energy space will go to zero of the perturbation. Okay? This is nowadays called conditional asymptotic stability. All right. Well, global asymptotic stability would be the statement about the L, for instance, about the L infinity norm. All right. So let me explain how the proof goes. Okay. So this is just an outline, just to give you some ideas. So let's look at this this equation. So what we want to do is we want to somehow show that if if the initial data for this equation is small, then the solution in some sense goes to 0, okay? So the key object here is the method that we use is based on spectral information. So it's based on the information about the linearized operator. So it turns out, and so this is very important, what is the linearized operator? What is its spectrum? So its spectrum consists of point spectrum. Point spectrum has 0 as the eigenvalue. 0 is the eigenvalue that corresponds to just the derivative of the kink, okay? It's always like that. You just take the equation for the kink, you differentiate it, and you see that the derivative satisfies the homogeneous equation. So it must be in the spectrum. And this is because I take derivative, let's say, of the kink, which is an odd function, and it's increasing, the derivative will be even and positive, okay? So the principal eigenfunction is even and positive, and therefore, in some sense, doesn't bother us, okay? It corresponds to the translational invariance of the problem, and because I assume that the initial data is odd, this translational invariance is somehow mod out, and it's not relevant, okay? But what is relevant is the second eigenvalue, which corresponds to the explicit eigenfunction. In fact, I should say maybe that this operator, okay, is a classical operator. You can compute its spectrum explicitly, even if you change 3 to some number and square root of 2 to some other number. This is called Tosh-Teller potential, this potential, okay? It's a classical potential, and the spectrum for this Schrödinger operator you compute, okay, is known. So in particular, in this case, it is known. And the second eigenvalue is 3/2, and the second eigenfunction is odd, actually. It's explicit. You can write it's sine squared times tangent hyperbolic sec squared times tangent hyperbolic squared, something like this, okay? With some coefficient. Okay, it's not so important what is the exact form of this eigenfunction. What is important is that it's odd and it's localized, of course. And there is a continuous spectrum that starts at 2. So what we do is we decompose the original perturbation into the mode that corresponds to the first non-trivial eigenfunction y1, the odd one, plus the rest, and this is an orthogonal decomposition, okay? And now the 2 or 4 objects that I have to, 4 functions that I have to find are z1 is a function of time, z2 is a function of time, v1 and v2, these are functions of time and space. Now it turns out, and this is, we call it normal form, but it's not exactly maybe normal form as you know, the Poincaré normal form, but it's somehow related to that. It turns out it's more convenient to work, instead of working with z1 and z2, it's more convenient to work with alpha, which is z1 squared minus z2 squared, and beta, which is 2z1, z2. Okay, so what are alpha and beta? Well, if you take z1 and z2 to be, so you take z of t to be z1 of t plus I z2 of t, and you take z squared of t, then this is alpha plus E beta. Okay. So this is a way to see where alpha and beta come from. All right. So you try to write the equation or the system of equations for z, z1, z2, and v1, v2. But as I said, it's more convenient to try to write the system for alpha and beta. So if you try to do this, you get an equation for alpha and beta, which is very nice. So it's basically linear. It's a kind of turning Hamiltonian system with some nonlinear part, which I noted by 3 dots. This is not so important. Okay, what is important is the linear part. Okay, so this is sort of like a harmonic oscillator for alpha and beta. And for V1 and V2, you have another equation, which is a system, where the system is coupled with this system through this function Z1 squared. So because it's convenient to write everything in terms of alpha and beta, one has to make, or one can make another change of variables, a change V1 and V2 to W1 and W2. Okay, this is just for aesthetic reasons more than anything. And then you get a system, again, for W1, okay, and alpha, and they are coupled with this function f, which is explicit, okay? The function f you can compute, and the function f doesn't depend on W. So in some sense, up to main order, these two systems are coupled linearly, okay? So this is something, well, of course, there are nonlinear parts. This is very hard maybe to control, but let's forget about it for the purpose of this talk. Let's think that there are only linear parts. So what do you do? So what we actually prove is more than just the fact that the perturbation goes to 0. We prove that the integral of z to power 4 plus the integral of w over space over finite interval, okay, and this square, that this is finite, okay. So you see that there are different rates for the part which is what is z to power 4. Z to power 4 is like alpha beta to power 2, okay. So there are different rates of decay for alpha and beta and for w, okay. The part that is related to z, which is called, that part is called internal mode, decays slower than the radiation, which is related to w, okay. So numerically, the decay rate should be like T2 minus 1/2, which is with agreement with this Z to power 4, okay. And for some problems, you can numerically show this, not prove it, but numerically show this. Now, for problems where there is no internal mode, there is no this Z part, in fact, you can prove, or there are proofs that show the decay like T2 minus 1/2 in L infinity norm, okay, with some logarithmic correction in the phase. That's not so important, but anyway. All right. So how do we prove this kind of result? So the proof is based on two they're called virial identities. So the virial identities, this is like using Lyapunov functional for the heat flows, for instance. So these functionals, they play this kind of role, okay, but that's not exactly the same way. It doesn't work the same way. So the first functional, maybe I should explain. The first functional, it seems ad hoc in some sense, but it's not so ad hoc. This part of the first functional is the momentum, okay? It's multiplied by a function phi, which you have to choose. And then there is a second part, which is made, especially, it's somehow prepared especially, so that when I take derivative in time of this functional, I get a bilinear form, okay? B is a bilinear form in W1. So only in W1, although this functional contains W2. See, this is how it is defined. It is defined in such a way that when I take time derivative, I get rid of W2 and I only have W1. Now, the second functional is kind of ad hoc, although it has this feel of momentum functional as well. Okay, if you think about it, I mix alpha with W2 and beta with W1. So like the first coordinate here, W1 with W2, and here the second coordinate with W1, okay? And it couples. So when I take derivative in time of this functional, I get a mixed term and a term that is kind of explicit, okay? And this in these two functions phi and g have to be chosen somehow. All right. So the proof basically relies on showing that this bilinear form is coercive in this sense. Because if I can show that this bilinear form is coercive in this sense, and I forget about the garbage, let's say, the nonlinear part, what I do is I integrate in time, and this is finite when I integrate in time, and I have integral in time of exactly what I wanted, okay? Alpha squared is like z to power 4, and W1 squared local norm in H1. Okay, there is some work to be done because I need W2 and I need beta, but this is very simple. So what we did originally, about 10 years ago, with Ivan and with Claudio, we chose this function g in an ad hoc way, and we proved numerically, so with not numerically, with the, we showed that this bilinear form is coercive using some numerical computations, so numerical computations of constants. Okay. So because we have to go for lunch, I will speed up. So let me explain how this virial identity works. So you think of taking this equation, okay, and assume that L is a Schrödinger operator of this form. So it's dxx minus dxx plus a potential, and take phi to be x. Okay, if phi to be is x, if phi here is x, so I have x here, and I have 1 because phi prime is just 1. So when I take derivative, I get, now this is not legal because I don't know whether this object is finite when I take x, okay? But let's say I can formally do it. So when I do it formally, I get a very nice bilinear form indeed, okay? W1 derivative squared plus some expression that depends on the potential P, W1 squared, okay? So this is a very nice bilinear form. So if I can show that this bilinear form with this sign is, so just without the sign, without the negative sign, okay, that this is positive, I'm done, okay? The second virial functional is more complicated. The second virial functional, when I do a computation, I get something that has, so the g now is an unknown function. I take the derivative, I do the computation, and I do after a couple of integration away parts, and I get to this, okay? So here it would be very nice if I can get rid of this term, and I could get rid of this term if g were the generalized eigenfunction of this operator, okay? So we would like to define g as a solution to this problem, okay? This is not so easy. This can be, somehow it can be done, but with some care, okay? But the point is that if I get rid of this term, what I want is I want to keep this term. I want to keep what has L alpha squared. And this means that fg, the integral fg must be different than 0. And this is what is called the Fermi golden rule. So all this thing that I told you was to arrive to the Fermi golden rule. Okay, the Fermi golden rule is one of the hypotheses that we have to make. So now I explain maybe a little bit faster the new general approach. So I consider the same problem, but now I will consider W to be more general than just phi4, okay? I will explain in what sense. So I assume that W is a double well potential in this sense. So it looks like this potential, and this is nothing. You can always make it to look like this for two neighboring wells by changing variables, okay, by multiplying phi by some constant and changing time or something like this. Okay, so this is not a problem. And I assume that for this problem, there is a heteroclinic solution, a kink, connecting -1 and 1. I write as before perturbation, and I have this problem, okay? But now I insist, this is not phi4, okay? This is a general problem, and the linearized operator is this operator, okay? It's not explicit anymore. So I have to assume something about this. So I assume that, first of all, the kink, the derivative of the kink is in the spectrum. This is always true. But what is more important, that I assume that the linearized operator has one odd eigenfunction that corresponds to an odd eigenvalue, which is between 0 and the continuous spectrum. Okay, omega squared is the bottom of the continuous spectrum. In fact, what is allowed is another eigenvalue, but I will not talk about it. Okay. I assume also the Fermi-Golden rule, as I said. The Fermi-Golden rule means that there is a bounded function that satisfies this equation. Okay. Notice that it's not lambda squared, it's 4 lambda squared. Okay. It's 4 lambda squared. The 4 lambda squared is bigger, and it can be proven. Okay. The 4 lambda squared is bigger than omega squared. If there is a bounded solution to this problem, then 4 lambda squared must be bigger than omega squared. Okay, and I assume that this bounded solution satisfies certain integral inequality, let's say. Okay, so this integral is different than 0. All right, and y, notice that y is exactly the second eigenfunction. Okay, the terminology, the Fermi-Golden rule, comes from Seagal. All right, and there is a new element. So I have still 5 minutes, I think. There's a new element in the proof that, because now the problem is not explicit, I have to introduce some new idea because I cannot explicitly compute anything anymore. So this new idea is called Darboux factorization. The Darboux factorization comes from Darboux, and this is an observation that if you have a Schrödinger operator in, let's say, in 1 dimension, you can factorize it as a product of 2 operators. Okay, so in this context, I think Dave and Trubowitz were first to notice the importance of the Darboux factorization. There's a paper of Chang, Gustafsson, Nakanishi, and Tsai, and we used it, I think, for the first time in our work in a paper with Claudio as well for the nonlinear Klein-Gordon equation. So what is the Darboux factorization? So remember, H prime, the derivative of the kink, is the first eigenfunction of the linearized operator, always. And this is a positive function, so it makes sense to take this operator. So in this operator, what I do is I multiply from on the right by 1 over h prime, then I take derivative in x, then I multiply by h prime. So it all makes sense, okay? So this operator I call u0, and then u0 star is just the adjoint, okay? It's the formal adjoint of u0. And you can directly calculate that L, the linearized operator, is the product of u0 on the right with its adjoint, okay? So this is what was already observed by Darboux. And what is interesting, in fact, is to take this product in the opposite direction. So let's say I start with u on the right with the adjoint u0, and then I multiply by u0. And this turns out to be another Schrödinger operator, okay? Nice Schrödinger operator, very explicit. I call this operator L1, and I note this is nothing, this is a triviality, that L1 u0, okay, is u0L. That is, u0 gets transferred, but not with L1. It doesn't commute with L1. It kind of commutes, but with L, okay, in some sense. You see? So this is very easy. Now, L1 also has spectrum, and the spectrum is explicit. If I know the spectrum of L, I know the spectrum of L1. It turns out that L1 has one eigenvalue less than L. Indeed, its principal eigenvalue is not H prime. H prime is not in the spectrum of L1, but what is in the spectrum of L1 is UZ is Y multiplied by U0, okay, from the left. Y is the second eigenvalue, second eigenfunction, sorry, of L, okay? And this I call Z, and Z is the principal eigenfunction of L1, therefore it must be positive. Okay, if it is positive, then I can play the game of factorization, but now with L1 and Z. So I define new operator U1 is very similar to the one before, but instead of H prime I have Z. Okay, I define it's a joint, and now L1 is not exactly the product of U1 star U1, but it's lambda squared plus U1 lambda squared is the first eigenfunction, the second eigenfunction, second eigenvalue, okay? And I define L2 similarly. I take lambda squared, but I invert the multiplication. Instead of taking U1 star U1, I take U1 U1 star. This gives me another Schrödinger operator, it turns out, with a nice potential. Then this potential is in some sense explicit as well. Okay, and I have the following. I can multiply L by U0 U1, and this turns out to be transferred with L2 to the right. Okay. So in some sense, it means that what I can do is, instead of working with the problem for which the linearized operator is L, I can work with the problem for which the linearized operator is L2. All I have to do is to multiply or apply these two operators, okay, to my linearized problem with L. All right. And the hypothesis, okay, it looks a little bit mysterious, but I will explain where it comes from, is that there exists a gamma such that this operator has at most one negative eigenvalue, okay? So this, if it doesn't have negative eigenvalues, it's okay. If it has a negative eigenvalue, it must be even, and therefore it's not bothering me from the point of view of perturbations that I assume to be odd, okay? And oddness is preserved by applying twice this operator, because it's like taking two derivatives. Two derivatives of an odd function is an odd function, okay? So let me explain where this comes from, okay? No, the other way. You see, it comes from this calculation. It's the same term. When I take the virial identity, okay, this functional, I derive in time, I get this functional, and it has the same xp prime, okay? This xp prime no, I go the other way, sorry. This xp prime is the same as xp prime 2, okay? It comes from the same calculation, okay? So what is the result? The result is under this three hypotheses. So let me remind you, the hypothesis is the spectral hypothesis, the Fermi golden rule, and the third hypothesis is this one. Okay, it's this hypothesis. Under this three hypotheses, I show that the initial data is a odd small perturbation of the kink, then the solution to this problem, okay, satisfies this identity. So the limit, as t goes to plus or minus infinity, it doesn't matter because the problem is reversible in time, of the local norm of the perturbation, local energy norm of the perturbation goes to 0. Okay, so this is the conditional asymptotic stability. So just let me give you some examples. So one example is the phi4 model. For this example, the three hypotheses can be checked directly. Okay, the spectrum is explicit. The Fermi golden rule, in fact, we calculated in our first paper by numerically, but it can be calculated explicitly, and the Lord and Masmoudi did it. Okay, it's a little bit of complex analysis. And then P2, this potential P2 is explicit in this case. It can be also checked directly. Okay, but what you can do is you can perturb phi4 model. For instance, you can take what is called phi8 model. So this is phi8 model. So phi4 is just the potential is just the first part, this part. Okay, I multiply it by another quartic polynomial. So this is a 8th order polynomial. And for this 8th order polynomial, I take m to go to infinity. So it means so this phi8 model has 4 wells. Okay, at -1 and 1 and minus m and m. So this is the phi8 potential. And you see that these two wells, these two, the leftmost and the rightmost well, I take to infinity. And these two wells are fixed. So in some sense, okay, made precise, this phi8 model when m goes to infinity converges to phi4 model, at least for the kink that connects -1 and 1. Okay, and for this kink, I can prove, I can show that the assumptions, the hypotheses are satisfied. The same hypotheses are satisfied by a perturbation argument. Okay. So finally, okay, some literature. So there is a rich literature about this problem. So I mentioned here, there's a work of Luhrmann and Schlag. There's a work of Alejo, who was visiting here not long ago, Claudio Munoz, is our Claudio, and Palacios, who is now a postdoc, but he was a student here. There is a work of 3 Chinese, Chen Liu and Lu. There's a lot of related work from different point of view by Lindblad, Luhrmann, and Sofer, Lindblad, Luhrmann, Schlag, and Sofer. There is a Kukania and Maeda. They work with problems with more than one internal mode. There's a work of Delort and Masmoudi. They provide finite time asymptotics. And there is a German Pusateri. I mentioned the result when L infinity norm is like T2 minus 1/2. It follows, among others, from the work of Germain and Pusateri. And they use a different approach, okay? They use what is called distorted Fourier transform. Okay, so I think I'll stop here.
For your interest. Are there questions?
Thank you, Professor, for your talk. I have a question about the local asymptotic behavior, like the limit of the t to infinity of the norm of U.
Yes.
What does it mean physically? It's like the initial profile is spread
It
out.
means physically that in this window Okay, this is, let's say, this interval I. Okay, let's forget about this part. After a long time, the solution will look like this, and the rest of the energy is radiated to infinity. So very far away, have a bump that travels to infinity.
Okay, thank you.
I was wondering about the case with more internal modes, Kukanya and Maeda, or also if these techniques, if you do one mode, that you transform.
Yes, what happens is that in this case, you have to check the Fermi-Golden rule, or analog of the Fermi-Golden rule, which is very complicated. Now it becomes, after more, once you have more than one internal mode, the Fermi-Golden rule becomes very complicated. It's not explicit anymore. You cannot compute it for any reasonable model. So in my opinion, this work of Kukanya and Maeda is useless. Yes, like for any model that is true. They assume, they have to assume. So this is different.
Sorry, may I ask a question?
Yes.
Do you hear me? Okay, nice talk, Mike. I would like to ask about this limit that you just talked at the end, m goes to infinity, because as m goes to infinity, the energy barrier between 1 and -1 also goes to infinity.
Yes. What happens is that you have to make a transformation, so it's not so simple. It's not.
Okay, we can
not,
divide W
yeah,
by
you divide
square,
by
something
you
like that.
divide by m, and you make change of variables.
Okay, then
So
okay.
so in such a way that the problem is a true perturbation of the FIFO model. So you have to work a little bit, but it's not so difficult. It's very easy.
Okay, thank you.
Do the decreasing of L infinity norm with the code T minus 1/2? Is it possible to prove this result? Do you think it's possible? When the interval increase with time, with the
No,
power.
you can increase a little bit the interval in time, but not too much. Okay. So I think you can maybe do something like maybe t to power alpha, where alpha is less than 1/2 or something like this. Maybe square root of t. Maybe you can do an interval like that, but not better than this. So you are you have to be very far from the light cone.
Like 2.5 t.
Yes, I think that you can take, instead of fixed interval, you can take interval that depends on time. Maybe the length of I of t is like t to 1/2, or maybe less than t to 1/2, something like this. I don't know, but not better than that, certainly.
That you have some physical motivation behind that represents something because you have them.
In which potential? In this one? Yes, there is a physical, they count high energy. Yes. Yes. For the kink, I don't know when unstable. Okay, yeah, okay, I understand the question. Thank you, Hannah. Yes, for sine Gordon, it doesn't hold, because for sine Gordon, you have a periodic solution that behaves like kink, so it cannot be asymptotically stable. So of course, we cannot prove it because we cannot prove for any of these potentials the hypothesis. Okay, we cannot check that. But basically, the conjecture would be that the only model for which there is no asymptotic stability is sine Gordon. Thank you. Unpack.
Okay, thanks again for.
Okay, thank you.
I prefer.
Yes.
My English is not very nice.
Puedes preguntar en español.
Perfecto. Pasa